31st for this semester of the postgraduate forum. This forum is run from the Vice Provost for Graduate Studies and Research and Development, Professor Sharam, and it's in the second semester. Each week it is run between the hours of 12 to 1, where graduate students get the opportunity to present some highlights of their research work or some other topics of their interest as part of the camaraderie and the build-up of a wonderful and great postgraduate environment. Today, it is my distinct pleasure to introduce a student who is working in the ever-popular area of research, bioenergy, and more specifically, bioenergy, of which I am part of the supervising team. And this young lady has done tremendous amount of work, which she might allude to later on. Our speaker today is Ms. Ria Mahmood. Ria has a master's in biology from the University of Bath. She was a former teacher in Cuba, the Holy Faith Convent in Cuba, and she is now a full-time postgraduate student of a PhD program in bioenergy from Algae. It is my pleasure, as I said, to introduce her today. Her other co-supervisors, Dr. E.J. John and Dr. Watson, will be a bit late, but they will nevertheless be here to join. And just to say that bioenergy research at the university involves research not only in algae, but also palm oil, coconut oil, moringa, and jatropha. The oils have already been produced, have been expressed, and work is also being undertaken at the undergraduate level for the testing of those oils, particularly the jatropha oil on injury. So, without further ado, let's all welcome Ria.
Good afternoon. I am Ria Mahmood. I'm an MPhil PhD student here at the university. I am based at the Waterloo Research Center, and I'm here to talk to you today on the potential contribution that algae can make to our future energy requirements in Trinidad. Okay, just a brief outline of the chat today. I'll talk to you a bit on energy consumption worldwide and here in Trinidad, a few facts on biodiesel, why algae is generating so much interest, what I've been up to as part of my research, the challenges that algae biodiesel faces to become commercialized, but highlight some of its achievements, and a round up with a conclusion. Right. As everyone here is aware, most of the world's energy is derived from fossil fuels, namely petroleum and coal, and to a lesser extent, natural gas. But there is still a need to reduce our fossil fuel consumption for mainly, one, to conserve our supplies, and two, to reduce our carbon emissions, because it is widely believed that there is a correlation between level of carbon dioxide emissions and climate change. However, bodies such as the World Energy Outlook actually predicts that energy consumption is actually going to increase by as much as 60% by 2030. The majority of this energy will be needed by developing countries, populous countries such as India and China, who are now at their stages of development, from becoming developing to developed countries. And it is also established that in order for societies to develop and to become advanced, energy is required. So the dilemma we face is how to meet this increasing demand for energy without actually depleting our fossil fuel reserves and severely affecting the environment. Okay, a little closer to home now. Trinidad is, of course, also heavily dependent on fossil fuels because it is readily available. But we ourselves need to reduce our levels of fossil fuel consumption, or to start to monitor it, because even though it's debatable, reports such as the Ryder Scott, which says that we only have around 10 years or so left of energy, is cause for concern or cause to take notice. And we are actually ranked 6th in the world in terms of our carbon index, around 28 metric tons per capita as of 2007. But no need to fear because we've gotten the ball rolling already. Our premier research institutions have already started research in our renewable energy areas, and I have personally listened to peers at UTT here who are working on projects of solar energy, wind, tidal, and biomass. Right. So among the renewable energy alternatives, biodiesel is fast taking interest, so becoming a premier option. Biodiesel falls under the subset of biomass energy, which refers to energy obtained from living matter or once living matter. Biodiesel is made from the lipids of vegetables, plants, or animals, and biodiesel is made by a process called trans-esterification, where the lipid obtained is also called the triglyceride because of the fatty acid and glycerol bonds, is reacted with methanol in the presence of a catalyst. The catalyst is usually like sodium hydroxide to produce the methyl ester, which is biodiesel, and glycerol, a byproduct glycerol. The biodiesel has been made from these sources, have been found to have properties very similar to conventional fuel. Properties such as the CTA number, which is an indication of how quickly, how smoothly the diesel combusts, the ease of how it ignites. Properties such as lubrication, density are also very similar. In addition, biodiesel has the added environmental bonus of being non-toxic, no net carbon emissions, and it can be produced domestically, which greatly reduces the risk of calamities occurring while being transported, such as oil spills across seas. Alright. Among the precursors for biodiesel, algae is generating a lot of interest for numerous reasons. They are, of course, abundant photosynthetic organisms. They fall into two categories: macroalgae, which is the cellular kelp, which everyone has seen at the beach at some point or another, and the microalgae, which is what we are interested in. And microalgae have a few, some of the properties that make it worthy of research is that it's aquatic, so it's easy to be cultured. They're very resilient, so they can be grown in very harsh or arid, barren environments. They require CO2 for their photosynthesis, so they absorb carbon dioxide even though it emits it. It has a very high reproduction rate. Some species can double within 24 hours, and the main reason it can do that is because of their simple unicellular structure. They are very efficient converters of solar energy. And some species have been found to have a lipid content of up to as much as 50% of their total dry weight. And microalgae lipids have been used to produce biodiesel, good quality biodiesel. But the main reason that algae is generating so much interest is its ability to help address this food for fuel conflict, where algae, because of its resilient properties, it can be grown on non-arable land, so it doesn't compete with food crops, and actually per hectare, and because of its high reproduction rate, per hectare it is thought that you can obtain as much as 50 tons of biodiesel from algae per hectare, compared to a competing crop such as the tropa, which can produce around 2 tons per hectare. Now, again, closer to home, so to sort of streamline to my project, algae research in Trinidad has been very limited and mainly focused on macroalgae. By around 1960, researchers such as Taylor and Hart they categorized around 59 species of macroalgae. But these gentlemen were mainly visiting professors at UWI or custodian directors, botanic garden directors. So they did these characterizations more as a leisurely pursuit than just full-fledged research. And Richardson, around 1975, he conducted, I would say, the first major study to try and categorize macroalgae species. He added 74 new species by making collections all around Trinidad. And most recently, Duncan and Neelam made a comprehensive study where they sampled around 60 locations and added, I believe, more than 100 species, which are all fully published in an issue of Caribbean Marine Studies. But these are all mainly macroalgae species, so research on microalgae in Trinidad is really not underway until now. So in order to address what role microalgae can play for energy in Trinidad, what I'm researching on is what species of microalgae here have a high lipid content, and I've included high in inverted commas to highlight the fact that we will consider species that have around 15 to 20% dry weight lipid as promising or worthy of further research, because really and truly, because this is uncharted territory, we have no idea what is actually out there. So to answer my research question, I have to survey for and identify high lipid microalgae species, and when I've done that, to conduct further experiments on them to sort of optimize their growing conditions so that I get the most lipid out of them by varying their growth parameters. So this is how I'm supposed to do my work, and this slide actually highlights tasks that I've already completed in my work. I've collected water samples from various locations around the island with different water salinities and areas with different human activity. I've filtered the water and I put them on back to agar so that I could obtain uni-algal colonies. And I then chose colonies at random and transferred them to culture jars, so they now went from solid media to liquid media. And in the liquid media, they had the chance to upscale, also reproduce to grow, so I can have a stock culture, so I can start my experiments from them. And I've done a basic microscopic examination to discern the phenotype. So basically just how they look, so sort of try and place them on a genus basis for further identification. So what's left to do in the MPhil part of the project is to actually continue these growth and reproduction experiments and vary their growth conditions to sort of see which species can produce high amounts of lipid under these conditions. So I will be playing with pH, temperature, the light-dark cycle, which refers to the level of sunlight or the level of light the algae gets on a daily basis. So it can be grown on continuous light. I can alternate every 24 hours. Times differ in the literature, and the salinity of the media itself. And of course, while conducting these experiments in tandem, I will be extracting the lipids and measuring the lipid content under these various conditions. And the one that can prove most versatile will be, one or two that will be my candidates for PhD research. Right. I've included a schematic here to sort of give you an idea of the process of algae biodiesel commercialization from start to finish. And it's a long process, and we've just started. So you start off with growing the algae, so you provide it with its various requirements, sunlight, nutrients. Sometimes you can starve it of one particular nutrient and stimulate its metabolism to produce more lipid. After it's grown, you harvest cells. In order to extract lipid, you first need to rupture it. Rupturing can be done using various methods. After rupturing, you use solvents to extract your wanted compounds, so fats and sugars. But the solvents used for the extractions need to be separated. And when you form your final product or your lipid, it is actually trans-esterified, and then you have your final product biodiesel. The process is still faced with a number of challenges in order for algae to actually become commercialized. The main one is, of course, the cost of biodiesel compared to petrodiesel. Research now suggests that if cultivated in photobioreactors, which I will come to, per gallon, algae biodiesel will cost around 18 US per gallon, compared to around $2.60 for regular diesel. So there's a big discrepancy in the price. So a lot of research needs to be done to lower the cost of algae biodiesel so that it can compete with regular diesel. And because of I've shown you the numerous stages where research is being done on all levels to sort of help lower the costs around. And and I'll go into detail some. The media that algae is being cultivated in, there's established media for varying species of algae. So freshwater, marine, there's standard media to be used for them. But those media are made from very high quality lab standard chemicals. So that they're very expensive, using filtered water and the like. So now we have to look at producing media that's made from low-cost means. So we're looking at using wastewater, seawater, untreated water as a base, and then adding, maybe runoff fertilizer to add to that to sort of help reduce the cost of the media itself. The culture method that is used for the bacteria. The algae. Algae is cultured using 3 methods. In small-scale research, it is actually mostly used in batch culture, and this is where all the requirements are added to the culture vessel, so the nutrients, you inoculate your algae, and then you provide sunlight as required. You conduct your experiment for the specified period, a week, 2 weeks, and after which you harvest your algae. But on larger scales, you tend to find that they have continuous culture, which is where, when the system is set up, nutrients is added continuously at one end, and algae is being removed continuously at the other end. And there's also a semi-continuous culture where the same sort of addition and removal takes place, but it's on a more periodic level, so probably on an hourly, or daily basis. Where the algae is cultured is also very high area of research. Because we're talking about algae commercialization, we need to look at cultural facilities on a large scale. So we're talking about open ponds. Now, per hectare, an open pond costs around 100,000 US to set up. But the problem with an open pond is that you can lose a lot of water through evaporation. You have pollution from particles in the air, and you have contamination from other microorganisms which you don't want in your culture. Photobioreactors, on the other hand, allow a far more controlled environment to culture your algae, but it costs around $1 million US per hectare to set up. Though you can get yields of algae of more than 3 to 5 times than an open pond. The only problem, other than its cost, is that photobioreactors have, because of its enclosed environment, and obviously the algae needs sunlight, when the excess heat is in the system, temperature tends to rise within the enclosed system. We have a problem with high temperatures. So scientists now are actually experimenting with a hybrid system, so trying to combine an open pond and a photobioreactor system so that you can get the best of both systems. Harvesting the algae is also very important. At what time in their growth cycle? Algae tend to have a very simple, single cellular structure. So you tend to harvest the algae, or the ideal time to harvest it would be at its late stationary cycle, so when it's at its maximum size and would have the largest amount of metabolites in its structure. The method of harvesting is also important. Algae can be harvested using filtration, centrifugation, and flocculation, so you cause the algae to clump together. Research is indicating that centrifugation and flocculation will take importance as a method for harvesting microalgae on a commercial scale, though it is still very expensive. Centrifugation, for instance, costs around 100 to 500 US per ton to do it. Other challenges, so all along the process. To actually extract the lipids from the algae, lipid extraction can be done in various ways. You use chemicals. The most common method to extract in the literature is using blind dye method, where they use a chloroform or methanol solvent extraction. But it seems that every researcher has tweaked that blind dye method to their own liking, so there are numerous versions of that. You can also use N-hexane or supercritical CO2, but those I believe are much more expensive. The actual reaction itself, so to convert a lipid to biodiesel, this reaction needs a lot of research to help lower the cost as well, to optimize it. We can look at things like the type of catalyst to use. You can use acidic or basic catalyst, the amount of the catalyst, the type of alcohol to be used along with the lipid for the reaction. You have the temperature of the reaction, because of course, as most reactions do, the reaction trans-esterification proceeds at a faster rate at a higher temperature, but a higher temperature, of course, means higher cost. So they have to find a balance between a temperature that's high enough for it to proceed at a fast rate, but not so high as to be too expensive. We have to optimize the actual separation of the glycerol, the two end products, the glycerol and the biodiesel, so that the most use can be made out of both products. And last, and to me honestly, the most exciting is the actual genetic engineering of microalgae. I should mention that, so most of the things I've talked about, so pH, salinity, temperature, those are manipulating the culture environments of the microalgae, and the term for that is biochemical engineering, but genetic engineering actually refers to the insertion of a foreign DNA into the microalgae, and well, if it's successfully expressed, you have a genetic engineered organism. So what scientists are trying to do is to play with the triacylglyceride pathway so that you can promote lipid synthesis towards more lipid. And what they're doing right now is sort of trying to isolate enzymes that promote lipid synthesis. And for instance, they've already inserted a gene called HOP1 into chlorella successfully, and that allows it to metabolize glucose directly. But what they're finding out now is that probably transcription factor engineering might be more logical, a bit more difficult in the end, because transcription factor engineering, transcription factors are like the doors to the entire pathway. So if you can alter if you play with the transcription factor themselves, those are also gene sequences. You can alter the entire pathway from on top as opposed to playing with the individual sectors of the pathway. So they're trying to alter transcription factors so that the entire pathway could probably turn on for longer or more often. And that way that we won't have bottlenecks along the entire synthesis pathway, which is dependent on so many factors. So these are the main areas where active research is being done so that costs can be lowered for algae biodiesel. But nevertheless, progress has been made in many areas of the industry already. Algae biodiesel is a proven alternative for diesel and jet fuel. A great accomplishment really, it's just that we can't produce it in good costs for it. Strains have been developed that can actually produce raw algae oil into biodiesel with around 80% efficiency, which is excellent. Strains have been engineered which can be cultured outdoors successfully. However, the United States Department of Energy, which is heavily investing on this research because they are looking at algae biodiesel to sort of fuel their entire naval system and their army system. They suggest that it'll be about 10 years before algae can actually be commercialized. So to round up the topic and to just kind of start with the point, which was what can be mentioned, that is that we're very realistic about the research that I'm doing. Our hope is that we have the prerequisites here. We have sunlight and water, so there's no reason why we actually can't cultivate algae and produce biodiesel from it. But to the level that we do it, we believe that we could probably contribute to the overall energy requirements here, but probably satisfy a niche market as opposed to being a large player. Thank you very much.
Thank you.